Oh, well, now we're going to have a class that's kind of like the old format because we only have an hour and 15 minutes left. So it's like those kind of classes. Okay, well, I have here 8 pages of notes. My goal is to get through half of them, and then the other half on Monday. But we're starting a little late, so I don't know. But I need to give a preemptive hint on one of the homework problems, the last one, 13, where you're working in the vector space L2, 0, 1, and you're given a subspace that has a span of polynomials up to degree 3. And you're given a function cosine, and you're asked to compute, so call it f naught, which is a projection, the orthogonal projection of f onto v naught. So in other words, what linear combination of 1x, x squared, x cubed, so what polynomial degree 3 is the best approximation of cosine on the interval 0 to 1? Now the thing is, a projection of a general function f onto some space v naught, the definition that's given is this linear combination where you take the inner product of f with your basis functions, but there's one problem. That's what makes this problem more of a pain, is that the EJ are required to find an orthonormal basis, or required to form an orthonormal basis. And these functions, 1x, x squared, x cubed, they are not even orthogonal, let alone orthonormal. So to apply this definition with f equal to cosine, you need another basis for the space of cubic polynomials that is orthonormal. So actually, I'm going to write an alternative definition. For a case where the basis functions are orthogonal but not orthonormal, it's almost the same thing. You just have to remember to divide by the inner product of each basis function with itself, which would be 1 if they were orthonormal. So this is a more general form. So you need these orthogonalized. Now, you could use what I mentioned at the end of last class, Gram-Schmidt orthogonalization, to get an orthonormal basis that spans the same space. But I will, because this problem is a rather tedious one, because even once you do have the orthonormal basis, you still have to compute these inner products. And those are integrals. And how do you handle integrals of cosine in a polynomial? What integration technique do you use for that?
You don't use by parts?
Yeah, by parts. Several times. So I'm going to, so for this, you could use the shifted Legendre polynomials, which you can look up and get. Those would be orthogonal, not orthonormal. So like you look at the Wikipedia page for Legendre polynomials and scroll down quite a bit. Because Legendre polynomials are orthogonal on -1 to 1. Ones of shifted ones are orthogonal on 0, 1, which is what you want here. So that saves you a little bit of time. It's good to be aware of those families of orthogonal polynomials anyway. So I have no qualms about cutting out a little work for you, because I've still left some work for you. As far as the integrals are concerned, when I'm grading this, because this is a signal analysis class and not a calculus 2 class, I'm not interested in pouring through pages and pages of integration by parts to see like, oh, we missed a sign there or something. I don't really care how you compute the integrals. However, if you want to do it by hand, give yourself a challenge. That feel free, or or use software, like MATLAB's integral function or Wolfram Alpha or something like that. Because what I'm going to do is I'm going to check the coefficients that you get at the end, and make sure those are right. So now, well, the thing is, if you use this definition, you get the coefficients in this basis. So it'd be a linear combination of those orthogonal polynomials. If you wanted to, you could then expand that and then combine like terms and so forth, and then you get the coefficients in this basis. I would prefer this because this is actually a lot easier to check in terms of the coefficients. But so that's what I have in mind for that problem. So because I just picked this. Oh, it's a best approximation problem. Okay, I'll just throw it in there. And then I looked at it when someone asked me about it. I was like, oh, that's actually a lot of work. So, and not the kind of work that I prefer, or certainly the kind you would prefer. Just a lot of grunt work and so forth. I mean, that's not really what I'm aiming for. I'm interested in to know the concepts. In general, how to compute a projection. Okay, and what do you do if it's not orthogonal basis? You have to orthogonalize first. Okay, so, but I think the rest of the problems, from what I can tell, I guess some questions about them, aren't so labor intensive. So that'll help. All right. So now, on the third day of class, we're ready to start chapter 1. Okay. I'm not remembering when I would be in Europe and I'd see elevators that would have floor 0 and floor -1. Somebody tells me that would just weird people out in America. Okay. Now, so the thing is, since this is signal analysis, but from our point of view, signals are just functions of t. And of course, we'll be going back and forth between functions of x and functions of t. But if you're going to interpret it as a signal, chances are you want to think of it as a function of t. And that function has components with different frequencies. And we want to understand the frequency content of a function. So a Fourier series, and how I will write it throughout. There's different forms you'll see, but mostly this one. So f of x is okay. So we have a constant term plus the sum of cosine terms plus sine terms. Okay. And these, the coefficients, the a, k, and b, k, so these are Fourier coefficients. So certainly we want to be able to compute these for a given function f of x. And often we'll be working on the interval, like a finite interval like minus pi to pi, but we'll also see how we can work on a different interval if need be. And what does the behavior of the coefficients tell us about the function? That's going to be interesting too, because as k goes to infinity, for this sum to even be valid, the coefficients ought to decay to 0. But the rate at which they decay to 0 is quite telling about the function's behavior. Okay, so I'm going to give an example of how these kind of Fourier series are useful. That comes from PDEs. All right. So most of you have taken a PDE course. This will be familiar to you. So if you look at, for instance, the heat equation, let's say on the interval 0 to pi. Okay. And then we have some initial condition. And keep the boundary conditions simple. I'll set the values of the boundary at x equals 0 and x equal pi equal to 0. So these are Dirichlet boundary conditions because we are imposing values in the solution at x equals 0 and x equals pi. Okay, so how we can solve a PDE like this on nice constant coefficients and relatively simple boundary conditions is a technique that many of you have heard of called separation of variables. Okay, so I'll recap that. Okay, so I guess for some of you it's a flashback to last spring, Math 606. And for some of you it could be a preview of next semester. You can take 606 then. All right, so I'm going to assume a solution has a form where it's a product of a function of x and a function of t. So what you can do is substitute that form into the PDE. Go ahead and compute the derivatives with respect to x and t, which will be simplified in this case. So what you get is, take the derivative with respect to t, the x stays the same, and you only differentiate the t once. And then on the other side, you leave the t of t alone and differentiate with respect to x twice. X double prime, t. And then what you do is, I'm going to divide both sides by x of x and t of t. So now you get t prime over t is equal to x double prime over x. Okay. Now, left side is function of t. Right side, function of only x. There's no way that a function of t can equal a function of x at any value of t and x, unless both are equal to a constant. So I'm going to set these equal to minus lambda. And the reason I'm calling it minus lambda, I don't have to do that. But whatever constant you have, it turns out it ought to be negative. And the reason for that is, if it is greater than or equal to 0, is this whole expression, then there's no way you can satisfy the boundary conditions. Because what you get is, from these two equations, you get two ODEs. So t prime plus lambda t is equal to 0. And then you have x double prime plus lambda x is equal to 0. And this is x. And then you also have boundary conditions. X of 0 and x of pi must be 0. And if you set lambda equal to 0, that means that capital X is a linear function. The only linear function that's 0 at 2 points is 0. We need a non-zero solution. If this lambda was negative, you can solve the ODE. You'd have a linear combination of exponential functions, one growing, one decaying. And that also cannot satisfy the boundary conditions unless it's equal to 0. So here, this lambda has to be positive, so the separation constant is negative. So now we can get a non-zero solution. So from the ODE alone, you would get, I goofed here. I should call this lambda squared. That ensures that this whole expression is negative. Okay, so now let's rewrite the solution in a more convenient form. So x has to be some constant cosine lambda x plus another constant sine lambda x. But now I have to substitute in x equals 0 and x equal pi. So if I substitute x equals 0 in here, I just get a, because that's going to be 1, and that's going to be 0. So a has to be 0. So we can forget about that. Finally, if I plug in x equal pi, I get, I don't really care about b, but sine lambda pi must be 0. So the only way that can work is lambda, actually, we all have a natural number. So not 0. So in other words, this leads to a family of solutions that work with the boundary conditions. So that would be sine, so I'll index these by k, sine kx. Okay. Oh, wait, make sure I'm getting all this. Oh, all right, yes. Yeah, so these are our solutions to the spatial part. Sine x, sine 2x, sine 3x, and so forth. So that's guaranteed to satisfy the boundary conditions. So in other words, lambda is equal to k. So now I can go back to my time ODE, and that tells me that tk of t is equal to some constant times e to the minus k squared t. So I don't know what this constant is yet. That will depend on the initial condition. So now what I can do is I can write, okay, my board use here is awful, I know. But, okay, well, I'll get rid of this stuff that's old. Okay. So, my solution, u of xt, is a sum of xk of x, tk of t, and now I fill in what that is. So I have, well, the time part I'll fill in first, and then sine kx. So my solution has this form. But now if I substitute t equals 0, oh, sorry, I forgot to beat k. Okay, so now I substitute t equals 0. U of x0, which is bk sine kx, must equal f of x. Okay. So this is a Fourier series like I wrote down earlier. You don't have any cosine terms, and that's because of the boundary conditions, but we need to figure out what these coefficients are. So that's what I'm going to explain next. How do we get these coefficients for a situation like this one? All right. So the question is, this is not a PDE class, but we will have more problems like that from time to time. But questions about this process? All right. So it's because of the boundary conditions that we find our solution is a linear combination of signs, which then determines what the time-dependent parts are. But now, we boil down to this problem, how do we get these coefficients? Okay, so that's what I'm going to focus on now is for a given function, if we want to find its Fourier series on a given interval, how do we compute these coefficients? Unfortunately, it's easier than one might think because of orthogonality. Okay. Well, I guess these are board use wasn't quite as bad after all. Although going vertical and horizontal might not have been such a good idea. But the logical place to continue past this point would be to start going down here again. So, okay. Well, as far as what to erase, yeah, this whole thing's kind of a mess. So I'm just going to erase everything. Well, wait. Does everybody have everything that's on the board?
Yes.
Okay. Well,
Yes.
not you get it from the video.
You can get it from the video, or just go back to last semester's notes.
Oh, yeah, good point. Right. Yeah. The thing is, I spent 3 semesters in these teaching workshops for AQ. They gave me a medallion at the end. I'm now an AQ Distinguished Teaching Scholar, where we learn all these different techniques, and now that it's over, it's like, eh.
Well, PDAs are very. I've discovered that PDAs are very useful here.
Yeah.
There are some things one really shouldn't forget.
Yep. Yeah, and there's so many classes that involve them, but you don't have a chance to.
Yeah.
Okay. Come on. All right. So now to simplify matters a little bit. All right. So this is computation. Of Fourier series. So start on the interval minus pi to pi, just because it simplifies things. Then later I'll generalize the interval. Okay, so how to get the coefficients AK and BK in this form of function. Okay. Well, QuickTime crashed, so I need to quickly recap what I had here. So this is a form of my, and we want to figure out how to get the coefficients AK and BK. So what I was result I was writing when I discovered the crash was this. Cosine, if you're working on the interval minus pi to pi, that's very important. The interval is essential. You're working with cosine. Both functions are orthogonal. If n equals k, we have these values instead. X, exactly the same results. And then we have here, any cosine is orthogonal to any sine. Doesn't matter whether n and k are equal, not equal, doesn't matter. Orthogonal. Okay. So now what that means is, so these functions are orthogonal, not orthonormal, but that's okay because knowing it's orthogonal, all we have to do is normalize them. So what this says is the norm of cosine nx is equal to 1 over the square root of pi and also norm of sine nx. They're both equal to 1 over pi when n is a positive integer or negative integer. I just haven't covered a case where n is equal to 0. And that just comes from this. If I take the inner product of cosine nx with itself, by rearranging this equation, I'm going to get pi. So I'm going to take the square root of it. Oh. Duh. Square root of pi, not 1 over it. I'm going to have 1 over square root of pi when I divide by the norm to normalize it. Okay, so it's a good thing I talk through these equations at least to make sure that they're right. Dang it. Okay, and so when n is equal to 0, that's the norm of 1, and that is the square root of 2 pi. Okay. All right. So to get an orthonormal basis, we just have to divide by these norms, and we have our orthonormal family of functions. So what I can say is this family of functions, so rather unusual way, but you get the idea. So like cosine of any integer times x over square root of pi, with integers increasing in that direction, and then 1 over the square root of 2 pi, and then sine of any integer times x over the square root of pi. So starting with 1, 2, and so forth, increasing in this direction. Is orthonormal. All right. So this leads to the formulas that for all the coefficients, the AKs and the BKs. All right, so what I'm going to do is write this Fourier series in a rather unusual way to show you how the coefficients pop out, because I want to see how we're using this orthonormal basis, but then certain things will simplify in the end. How do you know these are orthonormal? I didn't go through the proof of this. So if you were to evaluate the actual integral, like cosine nx, cosine kx, that I'm in the middle of erasing, what you do is you use a product to sum formula to rewrite cosine nx, cosine kx, or sine, or whatever you have. And those product sum formulas give you a form for the integrand that you can readily integrate. Then you plug in the limits minus pi and pi, you see, oh, you get 0. So it's not very interesting. It's a Cal 2 exercise. I might have put something like that in the homework anyway. But okay. So yeah, it's not very difficult to show that these functions are orthonormal. Okay. Now, okay. Okay, I'll show you one example just for fun. Because you can write it as 1/2. You have cosine n plus kx plus cosine minus kx dx. So that product to some identity that gives you that. And you have cases for product of cosines, product of sines, or sine with a cosine. They're all covered. And those come from the identities for a cosine of a sum or difference, as you can see here. And now you can integrate, assuming n is not equal to plus or minus k. So we'll just make that assumption right there. So you get sine n plus kx over n plus k plus sine n minus kx over n minus k with limits minus pi and pi. But n and k are integers. So you plug in pi minus pi, sine of any integer multiple pi is 0. So everything just goes away. So that's how all of these work out. So that's it. It's a Cal 2 exercise. Okay. But sometimes those can be fun.
Could you use the even function definition just to bring it down?
Well, in this case, with cosine being an even function, that would only let you change it to be twice the integral from 0 to pi of the same thing. Yeah, you could. Actually, that's more helpful with one of the other ones when you get a sign in here, because then you can say, oh, immediately it's 0. And that will come in handy for us later. Okay. Now, so f of x is written as a linear combination of the orthonormal functions. So if we have these coefficients, I'll call them ak and bk tilde because they're not the same as the ak and bk. So we have 1 over square root of 2 pi. That's the constant function in the orthonormal basis, plus the sum ak tilde times cosine kx over square root of pi plus bk tilde sine kx over square root of pi. Now, all the functions I wrote in parentheses are orthonormal. So that tells me how to get the coefficients. So a0 tilde is 1 over square root of 2 pi. Oh, actually, okay. It's the inner product from minus pi to pi of f of x 1 over square root of 2 pi. Because that's how you get the coefficients. When it's an orthonormal basis, you just take the inner product of your f with your function, your basis function. Similarly, ak tilde is the inner product of f with cosine kx over square root of pi, square root of just pi, not 2 pi. I'll just take a 1 over square root and pull it out. Okay. And then, similarly, bk tilde is inner product of f with sine kx over square root of pi. So they're a constant factor of 1 over square root of pi out. Okay. All right, so those are our coefficients. But now I could stop there and say, okay, we have our coefficients, we know what they are, we're done. But there's one thing that's kind of cumbersome about this is terms, like say the cosine terms. Here I have a square root of pi in its denominator. And then in the coefficient ak tilde, we have the square root of pi in its denominator. And we don't really need to have all these square roots all over the place. Let's just combine those. So what we can do instead is think of it this way. A0 times 1. So instead of working with the orthonormal functions, work with ones that are merely orthogonal. Okay. So in other words, all the square roots will just combine. So, A0, what I'm going to do is I'm going to take this 1 over square root of 2 pi and move it from here into here to combine with this one. So it's 1 over 2 pi, no square root. So I'm just shifting factors around. Okay. And similarly, AK, I already have the 1 over square root of pi in the coefficients. And then I take this one from the basis function, I combine them too. So now I have 1 over pi, integral minus pi to pi, f of x cosine x, or cosine kx dx. And then similarly for bk's. So 1 over pi, integral f of x sine kx. Okay. Oh, sorry to whoever's watching. Okay. All right. I'll always move it eventually. But I guess it's always good to have a notes in front of you also. Okay. So this is get the whole Fourier series. So this is a form that we're using, and these are the coefficients. So compute these integrals, and bam, you have your Fourier series. And so the AK and BK, those are the Fourier. So questions about what happened here? But some can make it a little less cluttered if you orthogonal. So what's happening here is product of cosine kx with itself. Here, this pi is the integral of sine kx with itself, and then the 2 pi itself. So you can always just say, okay, we use the orthonormal basis, and then to take the inner product of f with my basis function by inner product of basis function with itself, and that leads to these denominators. So it's all the same amount of work either way, I guess. Okay. Now, all right. So that's for the interval minus pi to pi. So what if you have? Okay, this works. Not too much glare, I hope. And it's not even all that interesting. Instead of minus pi to pi, we work with minus a to a. So what happens is, in general, use this. If you just have this integral of this form, integral over minus pi to pi, and you want to rewrite it as an integral from minus a to a. This is just a substitution. So x is equal to pi t over a, so you just carry out the u substitution, and this is what you get. So this is what will lead to the formulas for the Fourier coefficients in that case. So if you write f of x as a Fourier series where you have this more general form of your basis functions. Make sure I didn't overlook anything on my previous pages. Oh, nope, I didn't. Okay. Then, using similar manipulations to what I did earlier, the minus pi to pi case, here are the coefficients. So it's 1 over 2a, integral from, oh, man, typo in the notes. For the limits, I actually have from a to a. So I'm saying the coefficients are all 0. So
hey, that's easy to calculate.
Yeah. So this is why I don't post the notes before class. Okay. Yeah, it's copy and pasting, I guess.
It happens.
Yep.
At the end of the day, it's just kind of hard to see what the code is saying.
All right, so cosine n pi x over a. And then bk is over a sine n pi x over a. Okay. Whatever the radius of the interval is, pi before and a now, that's what you have. So 1 here, 1 over a up front here. You have your f of x, an appropriate argument. So you can see if a was pi, you'd have cancellation. So these families of functions, these cosines and these sines, are orthogonal on the interval minus a to a. So really, yeah, you could use this substitution with the previous formulas to get these. So most things is not very interesting to prove, really. And you could show that these are orthogonal using the same approach that I did earlier, using a product to sum formula. Everything works out nicely. Okay. Okay. So. So do I want to do this example? Well, okay. I'm just going to do how far I can hope to get today. Okay, I have about half an hour. That's pretty good, actually. Okay. Yeah, I'm not going to do that example. It's not very interesting. I have more interesting examples later that I want to make sure that I get to. Okay. Now, so this is a case of still a symmetric interval, minus a to a. But using even and odd functions, we can also get Fourier series on interval of a form like 0 to a without too much difficulty. But yeah, for later pages in these notes that I'll cover on Monday, I'll have several examples to go through. So you definitely won't get shortchanged.
And by Monday, we will have all typed up latex pages of the homeworks.
I can dream.
You can. Oh.
Well, how many of you would consider yourself late to some degree? Or okay.
Well, it's useful.
I don't even have it on my laptop. I have it
Kiss boo. Kiss boo.
Funny. Okay. Well, from where you are now, you're going to make progress. Or else. All right. So this is something that you brought up earlier, an even function versus non-function. So, first memory on that. F is even. Shut up. Probably phony IRS again. Yeah, I've gotten a zillion calls within 24 hours. So I was like, okay, sure. So if you negate x, but that does not change the function value. So for example, cos even powers of x are even, so the name makes sense. And is odd. Negating x also negates tangent and odd powers of x. There are plenty of functions that are neither even nor odd, like the exponential. Okay, so what we get from this is if f is even, then you have the integral from minus a to a is twice equal to 0 to a. Now, and this is for anyone who ever will teach Cal 2 someday. Because it's easy to think, okay, so I've rewritten this integral as this integral. And for students in Cal 2 who are so sick of computing antiderivatives, you're going to think, well, what does that get me? I still have to do the same amount of work. I still have to come up with an antiderivative for this. Yes, you do. But when it comes time and you have the antiderivative and you got to plug in limits, plugging in 0 in a versus minus a to a, you want to do this because then there's much less chance of making a mistake. Because here you're plugging in minus a and a, make a sign mistake. You're just saying, I really want to make a sign mistake. Something to gain, even if it may not save you work.
But it saves you accuracy.
Yes, and that's what really matters. So, and then we have a one that really does save you time, and it is odd. Then the integral is 0. We had a faculty member at USM, who's not at USM anymore, honors Cal 2 students an integral, and the integrand was really nasty. And so one of them showed it to me, and I thought, well, maybe it's something where he had talked about even and odd functions. Maybe it's something where you recognize, oh, the function is odd. Therefore, you could say, oh, the integral is 0, be done with it. But that's not what he was doing. He actually intentionally gave a function that was neither even nor odd, so you simply could not do the problem, and he didn't tell them that. So it's pretty dastardly, actually. So,
I don't know any mathematician like that.
oh, they're out there. Okay, that's not why he is no longer at USL. But, he wasn't booted for that, but he left the school offered to pay him more, something that happens around here very often. I do have to throw this in here just for fun. So the following fall, after he left, I happened to bring this up to my Cal 3 class, and I said that he's gone on to a better place because he was offered promotion and department head and a very large raise. So this girl up front, who's a freshman, says very excitedly, "Is he dead?" And actually, that's actually not the most interesting thing. Scary, that was not the most interesting thing she said all semester. So, I won't even get to the rest of it. So, yeah, teaching undergrads is quite adventurous. Okay. So what, now that we have this, we can say the following. If f is even, then its Fourier series only has cosine terms. If you're working with the interval minus a to a. And, but even if you're working with a series of minus a to a, you can get the coefficients using only integrals on 0 to a, using this property here. Okay, so that's our case where f is even. And if f is odd, then its Fourier series, again on minus a to a, consists only of sine terms. What? Okay, so then bk is 2 over a integral of f times sine kx. And the reason that works is if f is odd and sine kx is odd, the product of odd functions is even. So then this integral would be non-zero. So the funny thing is, multiplication of odd and even functions is nothing like multiplication of odd and even numbers. Because multiplication of numbers, odd times odd is odd, and odd times even is even. But it's the opposite when it's with functions. So odd times odd is even times even is even, and even times odd is odd. Because of what it really means about the negation. Okay, so when you have an even or odd function, you want the Fourier series on that symmetric interval, and then you can get whatever terms are left using integrals from 0 to a that are less mistake prone instead of from. Okay. And I give an idea in the notes of how you can build off of previous results. Well, and the formulas that I gave. Not interesting enough to really talk about beyond that. Or I'm just being lazy. And how am I doing on time? Okay. So, actually, I'm being good enough to not have pressure to cover too much on Monday. What?
I was asking if you are done with half of the AP.
Oh, I'm almost to that point.
Oh,
But the thing is, stopping right at that point, I have to go a little bit onto the 5th page.
oh.
Okay. But considering it started 15 minutes late, that means I'll have even less to cover on Monday. But again, okay, speaking of which, since there's homework due Monday, I don't know if anybody has other questions about the homework, or you haven't really done it yet.
Yeah.
Well, I don't have questions about the half that I've done.
Well, I would hope not, because you already turned it in. Okay, so maybe the best thing to do is, okay, I'll finish covering stuff in the last 15 minutes or so, but then it looks like we're going to have time on Monday for last-minute questions.
Okay.
And then I don't need to turn it in class. You can you can send it to me later or something like that. Yeah. So if you want to destroy your Monday night to finish it, that's fine with me. Because it's not like I'm going to be in class on Monday like I really want these things out. I hurry up and grade them because it's so much fun.
Because grading student work is just an entertaining experience, isn't it?
No. It's the least favorite part of a job. Yeah, I imagine for 101 it'd be even worse. But
Really, I can't imagine that.
Just wait until you have to give partial credit on an exam.
Well, I do have to do that for 102. Okay.
I'm just being sarcastic.
Okay.
I've graded in
Sorry,
the
I
past.
can't tell when you're being sarcastic and when you're being serious.
All I have to say is English.
Okay.
Talk.
Okay. So it's a very, very simple algorithm.
At least with math, there is a right wrong answer and a wrong answer. I have to explain to people why something's crap.
So I was just remembering how when I was in high school and taking British literature, I was reading an excerpt from the original Beowulf. Okay, yeah. And so after they slayed Grendel, and so what was actually written was that Beowulf stood up and quote and said, and I quote, said a few words, and he goes on for pages and pages. So with that in mind, I'm going to say a few words about functions on a half interval. Suppose you are working in interval 0 to a, and like you have a function like this is your f, and you want just on that half interval. Now there's a couple of different ways you can go about it. So you can extend it. So to fall back on the formulas that I just gave you, you can extend it in such a way that it's even. So I can define fe of x is equal to f of x on 0 to a, and f of on minus a to 0. Now, one nice thing about that is it will certainly make it continuous. Now, the other option is I can extend in an odd fashion. So FO of x is equal to fx on 0 to a, and minus f of minus x on minus a to 0. So as we see in this particular example, that will lead to a discontinuity unless f of 0 happens to be equal to 0. Then it will hook up nicely. So if you use either approach, so if I use this, so this is called an even extension, and this is called the odd extension. Okay, so if I use the even extension, I will get a cosine series. So FE would just be A0 plus a sum of AK cosine K pi x over A. And actually the formulas that I gave, they're these. It's exactly this. So I'm not going to repeat them. Okay, so, and what's nice about the definitions that I gave earlier, although I would suggest if you're taking notes to point to those, just so it's clear which A, K, and B, K are the right ones. And why does these definitions particularly nice? Okay, actually, it is on my screen. Good. So, yeah, these. Here's your. So if you're watching at home, this is your A0 and AK. I'm not going to write them again because I'm lazy. So if you really want to, you can. Because notice, I only want a series. I only need a series from 0 to A, and this only uses values of f from 0 to A. So it's nice that you can use function values from the interval in which you want the series to get the coefficients. And similarly, if you want to work with the odd extension, so that'd be a sum of all your sine terms. So bk sine k pi x over a, using a bk that was defined earlier. So for convenience, whoops, come on, that. That BK. Okay. All right. We're gonna have time here. Okay. Well, I'm almost halfway through page 5, and actually, did I fill up 8 pages? Yeah, I did. Well, I'm going to post the full set of notes, even though that's risky because there may be mistakes in the remaining pages that I haven't covered yet that I'll have to fix on Monday. But it has homework problems listed in there too for the second assignment, which is, and that'll be due. Well, yeah, that'll be due a week from Monday. Okay, so yeah, I think this is a good place to stop.
Yeah.
So wow, we only had class for an hour and 5 minutes. So that's
Oh.
okay.